Good day, I'm Norman Wahlberger. In today's video, we're going to carry on explaining how the algebra of Boole is such an effective replacement for Boolean algebra for electrical engineers wanting to analyze circuits, a very important topic in the engineering landscape in the modern world. So this is now an alternative framework to the standard story that's taught at universities all around the world. So I'm presenting a really new alternative which is powerful and I think much simpler. But it's really going back to George Boole. Okay, so we're going to be looking at the following fundamental question today. When are two circuits equivalent? And the idea is we're not going to take the two circuits and draw up truth tables or express the outputs of those circuits in terms of all possible inputs. Rather, we're going to look for the canonical Boole polynumber that represents each of the circuits. And the two circuits will be equivalent, that is, they have the same outputs with the same inputs, precisely when their Boole polynumbers are the same. Okay, so for example, here are two relatively simple circuits, just with two inputs, A and B. And let's express the output in terms of A and B. So for X, what's happening here? Well, here's an XOR gate, which corresponds to just addition in the algebra of Boole. And what are we adding? Well, the input here is a not A, because that's an inversion, okay? It's the negation of A. And here we have B. Now, in the algebra of Boole, negation is not obtained with a bar, okay? It's obtained by adding 1, because we're working mod 2. That's how you invert in the algebra of Boole. So the input on this side, on the top here, is 1 plus A. That's the input. The input here is B. And what are we doing? We're taking a sum of those. This is an XOR gate, which is just addition in the algebra of Boole. So it's 1 plus A plus B, which is 1 plus A plus B. So there's the canonical Boole polynumber that represents this circuit. Okay, here we have a NAND gate, and input A and not B, or 1 plus B. So how do you express a NAND gate? Well, if the inputs are, say, C and D, then the NAND gate outputs 1 plus C times D. It's like the product, which is an AND, inverted by adding 1. Okay, so we have to take 1 plus the product of the two inputs here. Well, there's one input, which is A, and the other input, which is the inversion of B, which is 1 plus B. And when we expand that out, what do we get? We get 1 plus A plus AB. Okay, so there's the Boole polynumber for this circuit. There's the Boole polynumber for this circuit. Are they the same polynumbers? This is just looking at them as polynomials. Polynomials in A and B. It's a year 9 question. Is this polynomial the same as that polynomial? It is not. They are not the same. So these circuits are not equivalent. Okay, very simple. And today we're going to be looking at more examples like this, hands-on, getting experience, working with gates, converting things into Boole polynumbers using the algebra of Boole. So in Boolean algebra approaches, this question of deciding whether two circuits are equivalent is actually quite subtle, in fact difficult. And the reason is because there's in general not a unique way of representing a circuit with a Boolean expression. There's ways of taking one Boolean expression and transforming it using various identities like De Morgan's laws, and there's a whole range of them, into something that looks possibly quite different. Okay, and so you could have these two expressions which are actually equivalent, but going from one to the other is kind of a subtle art. Now, in engineering courses, engineers are taught this subtle art, and it takes quite a lot of experience. But for us, it's not necessary at all. So we're going to avoid the difficulty here, because in the algebra of Boole, this is an entirely straightforward, even mechanical process, requiring no trickery or no cleverness or no fancy theory. Okay, we just use year 9 polynomial algebra simplified. Okay, and the ultimate reason is because the Boole polynumbers which capture the circuits are always unique. Okay, this is such a powerful distinction between the algebra of Boole and the Boolean algebra. If you're an electrical engineer, please contemplate this. Okay, it has huge consequences. All right, so we're going to take a hands-on approach today. We're going to solve problems directly, and you can follow my work. Hopefully it will be correct. Okay, our first problem is show that these two circuits are equivalent. Here we have a NAND gate, inputs A and B. Here we have A and B. We have inverters there, and then we have an OR gate. Okay, so let's write expressions. What is X? Well, that's a NAND gate. Inputs A and B. The output is 1 plus AB. Okay, what about Y? Well, Y is an OR gate with inputs 1 plus A and 1 plus B. So this OR is not the addition in the algebra of Boole, it's what we might call the circle addition. So I'm going to write this like this. The inversion here takes A to 1 plus A. The inversion here takes B to 1 plus B. And what we have to do is we have to take a circle sum between those two things. Okay, what is a circle sum? When we convert it into the algebra of Boole with just a regular sum and multiplication. Well, the answer is it's 1 plus A, the first one, plus the second one, 1 plus B, plus the product, 1 plus A times 1 plus B. Okay, squeeze that in there, okay? The first one plus the second one plus the product. Okay, what do we get when we expand that out? Well, the 1 plus 1 is 0. We get an A plus B. And when we expand this out, what do we get? We get a 1 plus A plus B plus AB. And the A's, there's 2 of them, they cancel. The B's, there's 2 of them, they cancel. We're left with just 1 plus AB. So yes, indeed, the circuit X and the circuit Y have the same Boole polynumbers. We've determined that just by doing this year 9 kind of algebra with this simplifying kind of rule that 2 of anything is 0. And we get the same polynumbers so that the circuits are equivalent. Problem 2, show that this one is equivalent to this one. Okay, so Z. What is Z? Okay, there's an OR gate with an inverter at the back. So that's a NOR gate. Okay, NOR gate. And the inputs are A and B. So how do you express a NOR gate? Well, an OR gate, we've just talked about, if it was just OR, it would be A plus B plus the product, AB. If it's a NOR gate, it means we have to invert that. Inverting means adding 1. So this is just 1 plus A plus B plus AB. Okay, that's what a NOR gate does to inputs A and B. That would be the OR gate. 1 plus it is the NOR gate. All right, how about W? Well, here we have an AND gate, which is just multiplication, and the inputs are 1 plus A and 1 plus B. So we just have to take the product of 1 plus A and 1 plus B. And when we expand that out, we get 1 plus A plus B plus AB. And yes, we can see that the output here, the Boole polynumber for Z, is the same as the Boole polynumber for W, so they are equivalent. So both of these are equivalent. By the way, the equivalence here is just sort of expressing a kind of a familiar identity at the level of the logic here, right? So we're taking this this inversion and moving it in front. So here we have, instead of having an inversion at the end of this gate, we have it at the 2 inputs in the front. And the effect is to change the AND to an OR. Here it's the same kind of thing. We have it starting with an OR and an inversion, and when we convert it, the OR changes to an AND the NOT here is moved to the other side, and there's two of them. So there's some kind of parallel between these two things, and they express a simple logic kind of identity. Okay, so problem 3, we have some more equivalences to show. So let's have a look at the first one, A here. So we have this output L. Let's see if we can write down an expression for L. So L is obtained by, there's an AND gate here. And the two inputs are what? Well, the top input here is the AND of A and B, and the bottom input is the OR of A and B. Okay, so we're taking the AND of A and B, that's just AB. Okay, and we're taking the product, because an AND is like a product, of this OR. What is an OR? It's A plus B plus AB. Okay, so what happens when we expand this out? AB times A is like A squared B, but that's the same as AB. AB times B is also AB, and AB times AB is also AB. And so the final result, after we cancel two of them, is a single AB. And we see directly that that's the same as the output of the gate M. So yes, indeed, those two are equivalent. Okay, how about this one here? We have A and B. Here there's an OR gate, an AND gate, and an OR gate. Okay, so let's write down an expression for N. So this is an OR. One of the inputs is A and B, which is the product AB. That's one of the inputs. I'm going to represent this OR gate sort of temporarily with a circle sum, because that's what we can use in the algebra of Boole to represent an OR efficiently. Eventually we'll replace that with what it's equal to, but right now we'll just put it there. And the other input is an A circle sum B. Okay, so when we expand this, let's maybe go up here, give us some more space. So when we expand this, let's expand this one here first, all right? So we have AB circle sum, and this A circle sum B is A plus B plus AB. Okay, now what do we have to do? Circle sum is the sum of the first one plus the second one, A plus B plus AB, plus the product. So the product of AB with A plus B plus AB. Okay, so there's some cancellations here. What are they? The AB here and the AB here, there's two of them, so they disappear. What happens when we expand this thing out? Well, each of these terms will be an AB. AB times A is AB. AB times B is AB, AB times AB is AB, so there's three of them, two of them cancel, we just get a single AB from this term here. And that will cancel, no, we've already canceled the ABs. So what we end up having is A plus B plus AB. And that's the same as O. This O here is just an OR. The OR of A and B is A plus B plus AB. Okay, one more. Here is P, and we want to simplify or show it's equivalent to this one here. Okay, here's the same O. That's why it's O also. It's the same gate over here. Okay, so what about P? What is this equal to? Okay, here's an OR gate, and the inputs are... Oh, I see I haven't finished the diagram. Sorry. Okay. We need some inputs, so we'll put this one here. Yes, and we'll put this one here. Okay, like that. So A and B are the inputs both to this AND gate and to this XOR gate. And then there's an OR gate that connects them. Okay. So what's happening here? We've got an OR gate. And the input, the first one is AB, that's the result of that AND gate. And then we have to circle sum that with this thing here. And this is an XOR gate, which is just a sum, A plus B. Okay, so now we replace the circle sum with what it's equal to in the algebra of Boole. That's the first one plus the second one plus the product, AB times A plus B. And what does all of that amount to? Well, there's an A plus B at the end. When we expand here, we're going to get AB plus AB, so they'll cancel, and there's still an extra AB out front here. And again, we're getting the same thing that we got in the previous thing, so that's the output O. So yes, indeed, these two are equivalent, and these two are equivalent as well. All right, in this problem, we're going to look at the equivalence between these two circuits, which is just a manifestation of the associative law of multiplication in our framework. And this non-equivalence when we replace the AND gates here with NAND gates. So let's have a look here. The first one here, Q, what's happening is we have an AND gate taking input A and B and other input C. So AND is represented by multiplication, so Q is just AB, that's the product there, times C, which is ABC. And similarly, R over here is, well, now we have the BC as one input, and the other input is A. Okay, we can put it maybe there. And again, we're taking a product, so we get ABC. And clearly these are the same, and it's just telling us that we can perform associativity. Okay, now what about when we replace the ANDs with NANDs? So over here, S, what is that? So it's a NAND gate. So a NAND of A and B would be 1 plus AB. So we have to take 1 plus the product of these two inputs. 1 plus. The top input is a NAND of A and B. That itself is 1 plus AB. That's that top input. And the bottom input is C. So here we're taking 1 plus the product of the inputs. That's the NAND. And that simplifies to 1 plus C plus A, B, C. Over here, T. It's another NAND gate between an A and this one here. So we'll write it as 1 plus A times the result of this NAND, which is 1 plus BC. The result is 1 plus A plus A, B, C. And we can see that these are not equal because as polynomials in A, B, and C, they're not equal. There's a C here, there's an A here. So sometimes it's convenient to use that identity that we've just had a look at and to introduce a variant of the gate allowing more than two inputs to it. So we could call these sort of triple input gates, okay? And we want them to be symmetrical so that they still don't depend on the order of the inputs. So here's an AND gate, and we see there's 3 inputs coming in, and this means that we're taking the cumulative product of all 3 things. So it's A and B and C, which algebraically is A times B times C. So that's what we got when we first combined A and B with an AND gate, and then the output of that ANDed with C. Okay. So that's just new notation that we'll introduce. And similarly, we can do the same thing for an XOR gate, which represents addition, because addition is also associative. A plus B plus C. If you do A and B first and then C, it's the same as doing A first and then B and C. Maybe a little bit less obvious is the OR gate itself, represented by us with a circle sum. So this thing here would represent A, circle sum B, circle sum C. And let's just check that this thing actually really is symmetrical. It doesn't depend on the ordering. So let's suppose that we introduce sort of a bracket here first so that we have a well-defined operation to algebraically simplify. A circle sum B is A plus B plus AB, circle sum C. So then we have to take A plus B plus AB plus C plus the product. We expand out. We get A plus B plus, okay, there's a C, there's an AB there. Then when we expand this out, we get AC, BC plus ABC. And there's no cancellation here because all these terms are distinct. And we see that it's symmetrical because it consists of sort of three separate parts. The A plus B plus C, which is obviously symmetrical if you permute the A, B's, and C's. And then these three terms is a little quadratic symmetric expression, AB plus AC plus BC. Again, unchanged if you permute things. And here is the unique cubic symmetric expression ABC. So once we have it expanded like this, then we see that in fact, yes, this does not depend on the ordering of the brackets. If we had expressed this as A plus B plus C and expanded, we would have gotten exactly the same thing. So that justifies us in introducing a triple input for an AND, triple input for XOR, and a triple input for an OR gate. But we're not going to do that for a NAND gate or a NOR gate or an XNOR gate, okay? Because as we saw, the associativity is not preserved for the NAND gate, so it doesn't make sense to have three things coming into a NAND gate and have a well-defined meaning to that output. Now in the course that we're putting together for this logic bool story, we're going to have a lot more examples, so there's a wide variety of things that we can do now in this general direction. But I want to illustrate the symmetrical aspect of what I've just introduced and the use of these triple gates. So let's have a look at these expressions, which are sort of manifestly symmetric in A, B, and C. So have a look at this configuration here. So we have A, B, and C inputs, and we have three AND gates. And the first AND gate takes an A and a B. The second AND gate takes an A and a C. And the third AND gate takes B and C. And all those three are then input into this triple input XOR gate. So what is the result of this thing? Well, it's an XOR. XOR is plus. And the output here is just the product A, B, because it's an AND gate. So what we're getting here is A, B, that one. This one here would be A, C. And the last one is B, C. So that's the output of that expression. And because it's symmetrical, I mean, we built it symmetrically. It's reflected in the fact that the bool polynumber that we get is symmetrical. Of course, we could have also built the same symmetrical expression in lots of asymmetrical ways, okay? But this is starting with a symmetrical circuit, and so the output should be symmetrical. Let's have a look at a variant of this. Here we have three OR gates, also hooked up to A, B, and C in the same fashion. So here's A or B, here's A or C, and here's B or C. And we're combining them with AND gate. Now an AND gate is multiplication, okay? So we have to take the product of three things. And what are those three things that we're taking the product of? Well, maybe we could write it out in terms of ORs, like circle sum. A circle sum B times A circle sum C times B circle sum C. Okay, let's convert that, as we want to do, into the algebra of Boole. The circle sum is replaced with what? So here we have A plus B plus AB. And here we have A plus C plus AC. And here we have B plus C plus BC. Okay, now we have some multiplication to do. Okay, so let's take the product of these two things here first. Okay, so this term times this term. So A times A is A plus AC plus another AC. Okay, that's going to end up canceling. Then a BA plus BC plus ABC. And finally multiplying by AB, AB, ABC, and another ABC. I'll put it up here, ABC. So all of that, okay, and we still have to multiply by B plus C plus BC. Okay, can we simplify this? So cancellations, ABC, ABC, they cancel. Here's an AB, they're canceled with that AB. Here's ACs, they cancel. And we're left with A plus BC plus ABC, I guess. Okay, so we have A plus, what did I say? Plus BC plus ABC. All of that times B plus C plus BC. Okay, so let's see what happens when we expand that out. Okay, A times this, so AB plus AC plus ABC, multiplying these three by A. Multiplying by BC. BC times B, BC times C, they both give us BCs, they're going to cancel, and the BC times BC will be another BC. Multiplying all three by ABC, we get ABC in each case. ABC, 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 so there's three of them. After cancellation, we just get ABC. And after the smoke clears, what do we get? We get AB plus AC plus BC, which is the same thing that we got up here. All right, since I don't have room, I'm going to leave it to you as an exercise to figure out whether this one gives us the same expression or something different. It should give us something symmetrical, but it's not clear which one. Here we have 3 OR gates, just as we did over here, but we have an XOR gate there, a triple XOR gate. All right, so check out what happens with this one. All right, so that illustrates some of the techniques that we're going to be using. We want to always convert everything to a Boole polynumber, and then everything is kind of cut and dried, and it's all just grade 9 algebra simplified. Simplified because 2 of anything is 0, and any powers can be rubbed off. So a year 9 student would be very happy to have to do algebra this way. Okay, in our next video, we want to address a very important issue for the Boolean algebra story, which is the dichotomy between expressing a circuit as a sum of products or as a product of sums. Okay, and so we're going to look at that from the point of view of the algebra Boole, where we see that the smoke clears and everything is light. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.